Good work, Bill. All right, we're gonna.
Was that recorded?
Yeah,
she said so. Good work, Bill.
It's a good work.
Bill, you did a good job.
Yeah.
We haven't recorded.
He's been on it with the recordings.
We can take that off. We can cut that out later.
I can edit.
Do a voiceover. Here we go. This is going to be similar to, well, yeah, it's the same presentation from yesterday. And we are looking at matter and its interactions. We did the video with, we used the same video for both 7th and 8th grade. We did a lot of similar things. We had we'll get into the modeling, the laminated cards. I just tried to think of other links to put in there, but they're throughout the slides. And Bill, it is the same. I think you had already put this presentation in. It's the same presentation as what yesterday was. You're going to see the materials that were used, and we'll quickly go through those. But really, we were focusing on the looking at properties of substances, both before and after they interact, to determine if a chemical reaction has occurred. And then also looking at conservation of mass, so that the total number of atoms doesn't change in a chemical reaction. And briefly, just that a chemical reaction is, you have your reactants, and you might have one substance, you might have two, it might be really complicated, but probably not for middle school. Don't make it too complicated. But they interact in some way. They form the different substances, which are the products that have different properties from what you started with. And that's a chemical reaction. That we're focusing on the basic types of reactions because they can be patterned fairly easily. And when students are, this is kind of like learning a new language for students when they're first starting with identifying chemical reactions. There is a lot for them to process in that. So I really like to start with the basics and show them how it's just following basic patterns. They're used to patterns, and so we can tell them, start with patterns and then use those then to start making predictions. Because eventually, as they go through, the capstone course that they have, at least, 11th and 12th grade, is then we're starting to predict what products can be made. And that is so complicated to do, but you have to have that solid foundation at the beginning, just understanding what those basic patterns are so that you can make those predictions. We really liked focusing on the baking soda and vinegar reaction for this whole kind of everything centered around that. For one thing, it tied really nicely into the geologic timescale video that you did yesterday. And actually probably a little bit into the air pressure demo too, really, if you think about the carbon dioxide. But we just like, it's a reaction just about everybody's done. And it's a very complicated reaction. It's not like, the students always want to know, but what is baking soda? What is it? Meaning what is the chemical formula for baking soda? And it's kind of messier than what you would hope it would be. It's not like a table salt, like an NaCl, where you have your two separate parts. First of all, it's got 4 different things going on in it. So that's what I mean. It's a more complicated reactant. But I think at its basic reaction, we can see the differences really well. We can feel the temperature change happening. We can see the gas being emitted. And then when we start breaking the chemistry of that down, it is complicated because it's actually 2 separate reactions in one. And we've linked this article here. I really like. I like this ThoughtCo. They have some neat articles just about different things. But this one talks about how baking soda and vinegar really is these 2 separate reactions. And we list those out. And then we see these 4 types. So where in the last slide, we talked about these 4 patterns. Here, we're showing examples of these 4 patterns. And there are so many other ones that you could show. But again, we wanted to show ones that related back to the video that we had done. So the double replacement, that is our first reaction we'll start with. Sometimes you'll see it as double displacement, replacement, displacement. It depends on who you're the source that you're looking at. But this is where you have your baking soda, which is the NaHCO3, and your vinegar, which is acetic acid. And that if you look at the sodium and the hydrogens are kind of nailed down. They're staying where they are, and they're switching those ions that they're with. And that's pretty complicated for middle school. Like, I wouldn't expect middle schoolers to necessarily see that without a lot of help and a lot of scaffolding to get that. But that's why it's the double replacement. That sodium, that hydrogen stay, and the acetate ion that you see that was here has moved now to the sodium, and then the carbonate, hydrogen carbonate, it moved over to make our carbonic acid. Then once we have our carbonic acid, and this article explains that carbonic acid is pretty unstable. It doesn't want to stick around very long. And that's where we get that decomposition of the carbonic acid, forming that carbon dioxide from that. And so when we did that in the video, that was really cool because you could see that baggie that we were using. It was just a Ziploc bag, but gosh, with the ratio that we put in for the video, it filled so tight. I was really worried it was going to explode everywhere. Like the camera went off and I quickly undid the zipper because I thought this is going everywhere. And we had put some bromothymol blue in that so we could see the indicator as the pH level changed. And we'll talk about that in another slide as well. But that was really cool to see. This is a decomposition reaction. And I think Stephen had remarked at the beginning, and this is a common misconception, I think, that you have to have at least 2 reactants to make a reaction, and you don't. And so that's this is a really important type of reaction, this decomposition. And it is a chemical reaction from just one reactant. And sometimes you'll even have one reactant breaking down to form like 4 or 5 smaller things as well. It just depends how large that beginning reactant is, and a lot of other factors go into that as well. But this is an example of our decomposition. The opposite of a decomposition is a synthesis. And the synthesis reaction that we focused on, just to be consistent, was the carbon dioxide into water forming the carbonic acid. And we show that in our video using some universal indicator. If you have some tap water that's going to register about a 7. So that's what we have. We had tap water. Our tap water is right around 7. We put that universal indicator in, and the color chart, it was just dead on where that 7 was. We blew some carbon, we just blew our breath through a straw into the flask, and it was just water and universal indicator. And it took just like a minute, maybe 2 minutes, and we saw that register, that color change. Now we're at a pH of 6. So we can see that pH dropping because the carbon dioxide that we're breathing into the water is mixing with the water and forming that carbonic acid. And that acid is dropping the pH level of the neutral water.
Erin mentioned that she liked the baggie, but usually doing that with like an Erlenmeyer and a balloon.
Yeah.
And I came from the elementary world, and we just didn't have Erlenmeyer. We didn't have glassware. Heck, we don't have glass anything. And so we just did everything in baggies and stuff like that when we did our science. And so that's kind of why when I came to Purdue and stuff, we started doing it in there more. But we didn't, like the big kids in the middle school teachers will have that glassware. Yeah. And
definitely easier cleanup.
Easier cleanup, but you will have more. You do have to be really stringent with the kids, as you said. When we did it, I mean, I was hoping it was going to explode. Let's face it, on TV. But you were a bummer. You took it away before it got to explode.
It's just years of training.
With the students, I mean, we more or less threatened them. Make sure you do all the air out so it doesn't go over. And if you saw one getting too big, we kind of had to go over. All right, let's open it up a little bit because look what's happening.
And no matter what, whether you're using the Erlenmeyer flask, or you're using the baggies, or you're just using the water and universal indicator, no matter what, we are wearing safety glasses. And that, I can never stress that enough. And I had so many kids over the years, it's just water. And I would always tell them, and when it's just chemical, you're going to be glad that this is a habit and that it's not getting into your eyes. You always use those safety glasses, even if it's just water, even if it's just, no matter what, so that you're building and developing those good safety habits so that you're prepared and you're ready, should anything ever go wrong. So it's just always important. I just always like to throw that safety part in there. And then single replacement. Speaking of safety, single replacement, one example is any of those alkali metals in water. And I don't recommend that. I never felt safe doing that ever in the classroom, but one of my best friends from college is also a chemistry teacher, and that was like her favorite thing to do. She felt probably too confident doing that in water, and she would do this all the time. But I will say that I did it one year. Flynn Scientific sells a really neat kit, and not that I'm endorsing Flynn Scientific, but it's really cool. And this is a link to the lesson that they have, and the idea behind it is so awesome. And so I'll just describe it since we're talking about single replacement anyways. It is forming those alkali metals with water form strong bases. And strong bases will turn, if you use an indicator like phenolphthalein, they can turn pink once they hit a certain pH range. And what this Flynn Scientific, what this kit does is it takes this long, like a large graduated cylinder, like a glass graduated cylinder, let's say, and you fill it a certain amount of the way with water, and you add a few drops of the phenolphthalein, which is clear in regular pH 7 water. And then you add a layer of mineral oil. And then they send you this, the little pieces, and they're tiny little pieces of sodium. But you get one of the pieces of sodium, it drops down through the mineral oil layer. And when it hits the water, of course, it has all this oil buffering it on top. When it hits the water, it starts jumping up and down because it's got that energy, right? And it jumps back up, it comes back down, it bubbles a little, jumps back up, comes back down, bubbles a little. And every time it interacts with the water and it's forming that sodium hydroxide, that strong base, slowly that phenolphthalein starts turning pink. And so you can see if you put a sheet of paper, something behind, or maybe you set it on a sheet of paper, you start to notice all that water down below is turning pink because that sodium is reacting with the water and forming the strong base. It is a really cool reaction to see when you can do it safely, but I know there are just so many opportunities for that one, especially to go wrong. So just really use a lot of caution, and I don't know if I would do it with middle school. I just don't know. But when you're talking about examples of single replacement, you get a little hard pressed trying to come up with something that's safe that you can also show happening. Okay, moving on. How do I know a chemical reaction has taken place? Well, a temperature change cannot be the only indicator of a chemical reaction. There will be other indicators also with temperature change. Temperature change could signify either a chemical or a physical reaction. Sometimes there's a chemical reaction and there's no temperature change. So it's not the only indicator. We're not just going to use temperature change. But if a precipitate forms, that's a chemical change. Then we know that's happened. We talked about a few of these examples within the video, the wastewater treatment plant, and how the chemicals are added, and then they precipitate some of the nasty stuff out of the water. It sinks to the bottom, and then that purified water goes on the water where that stuff has been extracted out of it goes on for further purification. Stephen talked a little bit about gold mining.
Yeah, mining in general. I mean, they break up the ore, they put it in chemical vats.
Yeah.
And actually, for that reaction, it forms effervescence and precipitates. Then they scrape precipitates off.
Yeah.
And so they scrape the top of that off with all the bubbles, and that is holding the different minerals that they're trying to mine.
And then even in our bodies, of course, there are lots of chemical reactions happening as well. I think we talked a little bit about the kidney stone and how you have these calcium ions and then oxalic acid, which is present in a lot of the food that you might eat. And that can result, it won't always result in a kidney stone, but it could. And then you had brought up effervescence, which is just the presence of bubbles or any gas formation. So we know a gas is forming if we see bubbles, definitely. We show in the geologic time scale, we show an up close picture of vinegar on chalk, and the vinegar test just in general for carbonates. Sometimes I know when I took an earth science class for my teacher training, we had used really dilute hydrochloric acid, and that's similar to vinegar and testing for the carbonates and limestone. Is it limestone? Is it not limestone? So seeing that bubbling happening, if you still have some chalk and you're able to show that with the vinegar, that is kind of neat to see for students to do, and that's safe, I think, for them to do as a demo with the safety glasses. Putting drops of that on. I like to use a 1 part baking soda to 3 parts vinegar for the vinegar and baking soda, whatever you want those parts to be. It kind of depends on how much room you have and in your container and that sort of thing, but that tends to have a pretty good outcome, that 1 to 3 ratio there. And then we've mentioned a couple times about the phenolphthalein and the universal indicator, that these are indicators that change color like at different pHs. It's not always all about pH. Sometimes you'll have other color changes happening just because you might have metals that are going from a solid state to an ionic state. And so you might get a color change for that reason. But yeah, so we talk a lot about pH color changes in the video. And I think in our kits, we had these tiny little dropper bottles of 3 different indicators. Universal indicator, so that's the one that we put into our water, and we use a straw and blow our air into the water. And that can drop the pH because carbon dioxide reacts with the water to make the carbonic acid, and then that pH level drops. We can see it there. bromethymol blue, which we use in the baking soda and vinegar reaction that we do in the baggie, and then also phenolphthalein. And we did show phenolphthalein just so you could see that it is a much more drastic color change that you can see, but the universal indicator is just changing from like a yellow to a green or a green to a blue. I forget which one it is. So it's not like a terribly drastic change. Phenolphthalein is a pretty drastic change. You're clear and then you're pink. Like this is just, it's clear and pink. There's a really small error right when it hits that turning point where it kind of is a little pink, and then it's just. And I like using that, and any of the indicators that you're using are all going to give the students kind of a taste of what a titration is kind of like. So even though they're not doing anything with titrations yet, it's just kind of leading them, and they're going to see this eventually. And so it's kind of getting them to that point that kind of building some of that background knowledge for them about why these are working. We also I would boil cabbage every year when I was still teaching. That was every year. I had my day when I would boil my red cabbage. I'd use an old milk jug. I'd take it in and we'd put that, a few drops of the cabbage on different substances like stain remover and laundry detergent and vinegar and bleach and all, and see what happens to the color of the red cabbage. I had no idea that there were so many other foods that would change colors with a pH change. So again, that's that thought code that we had talked about before, but they have a really neat edible pH indicators color chart. I thought that was super cool, and we also highlight that in the video. Let's go to the next. There we go. All right, so we have a couple of activities that we developed, and this was one Steve and I were kind of mulling over before the workshop. How are we going to show what's something we can do that has the kids doing something hands-on, that they're going to be able to show that all of the reactants turn into all of the products when we do this. And we got to talking about it and came up with this idea of using poker chips or some other different manipulative. We use poker chips, and so the supplies that we sent out were the poker chips. We made up a sheet of labels, and we made that link here. Maybe, yeah. So this is already, the link is already there on the slides. If you have used those little circular labels, I think there was like 30 of them on a sheet. I think we use the Avery labels, but I think there's other brands as well. So hopefully this will be helpful and you'll use this. But then you're going to see for each of the reactions, the number of poker chips that we're allotting for these. So my thought is
you could just print them out and cut them with paper cutter and have little pieces. You wouldn't have to put them on a poker chip thing.
No,
we just thought that added to it because it's
it gives them like a piece of
manipulative.
plastic. Yeah, it's easier to maneuver around, and plus it has the color. I kind of like having the colors. I thought I was getting the poker chips that had the 4 like red, blue, white, and green. I thought I was getting a package like that. It was red, blue, and white. So I just split the white poker chips. Some were hydrogens and some were oxygens. So, and that's fine. That works. But when we go to the cards, I guess we aren't there yet. Because I'm like, why don't I see this? Okay.
What are you doing here?
Sorry. Okay, here are the cards that we had. And again, these are going with those examples that we were showing in the video and that we were talking about in these first slides. This double replacement reaction, we would start with this card. Ideally, it would be laminated, but it's something that the students would have paper and pencil they could do. But you could also do this in Google Slides. You could import some shapes and make some things that the kids could click and drag over. So that's easy to do in a Google Slide presentation. But that we would have for the balanced reaction, and I think this is 1 to 1 to 1 to 1, that we would have the right number of poker chips to make both of these, right? The baking soda and the vinegar. And so we would say, okay, this is what our reactants look like. And then we're going to move all of those poker chips over, I just saw the button comment. That's a really good idea.
Buttons, maybe.
Buttons would be really cool.
I was going to say, yeah, you just have to make sure that we did a visual there so they knew which, like if you have the small clear buttons, those are the H. If you have, so which are which.
Yeah, but they can, any kind of manipulative like that is a good idea. And then we're reforming those, that we're making the sodium acetate and we're making the carbonic acid. And so that at the end, everything that they had available for the reactants, they've now rearranged to form the products, and they look different. They're in a different arrangement, but that they're all used. So we didn't come up with anything new. We didn't lose anything, that mass was conserved in this reaction. The other thing that I really like about modeling, whether you use the poker chips or the buttons or slips of paper or whatever manipulative it is that you're using, is that we're really driving home that particulate nature of matter. That students are thinking, here's my baking soda, and I can see it, but that it's actually made up of much, much tinier particles that we can't see, but that they're there. So even though we can't see them, it's still there. That's what we have these little sodium, hydrogens, carbons, and oxygens all bonded together to make that baking soda. And at this point, it doesn't matter how they're arranging it. It just matters that they know that they go together. The geometric, geometries for these, that comes later. This is just very, very intro, that we don't care. We just want them understanding that this set of poker chips goes together, this set goes together, and that they're reforming to make different products. And then we have that same idea for the other cards, for the decomposition, and then the synthesis, and then the single replacement. Oh, M&Ms
and Skittles.
Yeah, M&Ms and Skittles, that's good. And the kids love that as well, that they're using candies. Yeah, marshmallows. Yeah, no, you don't use. I think I use M&Ms a lot.
Everybody does with me. I think I'm the only person in the world that won't use food.
That's okay. We're back here.
Especially M&Ms. I mean, you'd be like, oh, where's this one go?
Yeah. I would use marshmallows. Marshmallows a lot for the air pressure, and so I'd have syringes and caps. And then we put the tiny little marshmallows in, and we show like how they shrink and they shrivel and they expand and that kind of thing for our air pressure demos. And I'd always have the kids like, I didn't get any marshmallows. It's because they're just sitting there eating them faster than I can give them. And that's funny. And then this was something developed from last year. And I had mentioned the periodic table lockbox earlier, but this was one of those activities incorporated with that. But I thought it kind of goes in with, we're talking about conservation of mass anyway. And we had talked about before that you could do a cut and paste with some images, like here on a Google slide, you can insert a shape. Really what I think what I did is I went into a separate Google Doc and I just typed in like AL, AG, and changed the colors and typed in some numbers. And then I used my snip tool. So down at the very bottom, or you can search for it in your computer, you might have a snipping tool. And if you click on it, and oh yeah, Jamboard is a good idea as well. You can definitely do that. But that you can cut and paste and make a picture that you see there. Everyone can see this, I think.
Yeah.
And then you can copy that in. I'm not going to save it right now, but then you can insert the picture here. And so where we see our slide, there's this margin on both sides of them. You can have those and then use those to manipulate them over. So you can click and drag them over.
Someone asked about the laminated card activity to be done prior to balancing equations.
I think so. I think that,
that's what I thought too.
Yeah, because we're not so much, we're kind of at that point with the laminated card activity, we're giving them the balanced equation ahead of time. So they might not even pick up on that there's two. They just know, oh, I have two red ones for sodium and then two of these groupings to make water. And
I think by doing that, seeing that, manipulating that would help me as knowing the type of learner I am.
Yeah.
I think it would help me when we get to balancing equations, be able to do that more successfully.
Plus, then it's something that they've seen, like you've been exposed to it
so much faster.
Yeah. So definitely, I would recommend that as well, but that's my opinion on that.
I think next year we do a lockbox, and if they want to come into activity, they have to do the digital online one, and the last lockbox thing is the code for them to get into the workshop.
But then they would be motivated to come listen to us talk to them. Is that their motivation?
Yeah.
We're not going to have any. Oh, coefficients and subscripts. Yeah, perfect. I understand. Yeah. The subscripts can get tricky, and especially at the middle school level, because you maybe haven't talked about diatomic elements. Easier way for them to memorize. What's the comment
Oh,
Let's see. Is there an easier way for them to memorize? And I'm not sure about
coefficients and subscripts. Maybe?
yeah, about the difference between coefficients and subscripts is the question. I know that subscripts get tricky. Yeah, okay, yeah. And I know like when, and I don't know that I don't know where you tell the middle school students. I'm not quite for sure, but they will see it. So maybe it is appropriate that when you're bringing up the periodic table, that you have certain ones that are the diatomic elements. So right, always hydrogen, and that just means it's never just an H. Like if you ever see hydrogen, it's never just an H. It's never just a Cl. That you never just have a Cl by itself. It's always paired together. But then you don't want to get too much into it because it gets confusing because it has to do with their energies and things. But it kind of makes a pattern on the periodic table. And so, periodic table. That we've got our hydrogen, and that we start with the nitrogen, oxygen, fluorine, chlorine, bromine, iodine. That it kind of makes, I always thought it kind of made like a 7. And that there were 7 of them, counting the hydrogen as well. So I would always tell them those are the ones that if you ever see them, it's always, you always have that subscript of a 2. You just have to, and that's just kind of one of those things you just have to know. But I have to admit the majority of my time was spent teaching the sophomores. So I don't know, trying to think back to middle school. I did teach middle school a couple times, but I don't remember. I just don't remember, if we covered it or not. But then so then iron is not one of those that we put down there. Coefficients and
photosynthesis.
Ooh, yeah. Ooh, that'd be a good tie in with that as well.
It's 8th grade, yeah.
Yeah.
That's it.
And at that, I feel like 8th grade probably, yeah, that's probably a good point to, and probably, yeah, that's where we'd be doing. I can't remember where it all falls with the standards. It's different for different places.
If doing photosynthesis, that's a good spot for them.
Absolutely.
For them to
Yeah.
understand. That makes sense. It's
Yeah.
logical.
And this one, we have the, conservation mass, right? Yes, so subscripts are like exponents, right? They're similar, and that your coefficients that you're kind of distributing, right? Distributing through. So when you put your coefficient down, like we know that we would put our 3 and we put our 2 here, and I'm not quite doing this the way I intended, where you'd put the way I intended is you'd put your division bar down, and then you'd click and drag over your 2 chlorines and your iron, and then try to figure out like how many of each one you need. But that these coefficients are those whole numbers, but then that they get distributed. So 2 for the Fe, and then 2 times 3 for the Cl, and that's how you're getting those. So yeah, those are all good points. So yeah, so I just had a couple of those just to show a different way of using, virtually maybe using with manipulatives to try to show balancing reactions. But
yeah,
I'm going to stop. Just to show, the division bar is just to show, yeah. So that division bar that I had was more just to show the students that that this is separating the reactants from the products, and that the idea was.
But doesn't the arrow do that? Why do you need that? Yeah,
the arrow does, but I think it's just the idea of just drawing it to like tell myself that, yeah, no, I'm really separating this out. Yeah, the arrow's there, but I don't know. It's for me, it's just kind of separating it off to the 2 columns.
That's okay.
And they're using, so here I would click and drag my 2 chlorines. And then you're going to see I have even more chlorine. So what I did is I cut and pasted a lot of the same one all in once, and they all kind of stack together. So then I just have like an infinite supply of them. It's not infinite. I think I run out eventually. But then I move my Fe over here, and then my Cl3. All right. And so then I know, okay, well, my irons are good, right? I've got 1 iron over here and 1 iron over here, but I've got 2 and I've got 3. So how can I need another one over here. Well, I can't just add 1, because when I add 1 over here, how am I going to, what times 2 is going to give me 3? Well, So then we're talking about least common multiples. So between 2 and 3 would be 6. So, okay, well, let's add 2 more here. So now I've got 4. Well, now that doesn't work, right? Because it's CL2, so I had to add them together in the pairs. So I go back over here and I think, well, I know that the first number or the least common multiple of 2 and 3 is 6. So I would add a few more chlorines.
Yesterday, you used poker chips. I have them use single punch and make a bunch of 3 different colors for atoms of photosynthesis. Kinesis.
Oh, that's a good idea. Yeah. So then I see I've got my 6 chlorines. I've got my 6 chlorines. But now I would need, because it's all together, I would need another iron. So I add over my other iron. And so now I know I've got 2 of these. And then I would need 3 of these. So that's kind of the idea behind it. Anyway.
I like the paper punch as a manipulative idea, though.
Absolutely. No, I do. That's
cheap
a really
and easy.
good.
I like that.
Yeah.
Like that.
Yep. All right. So that's what I got.
Girl wasn't as boring as I thought it'd be.
Well, that's good. You survived.
I
So
did.
that's good. Aw, great. Yeah. Yeah, thank you to everybody. We sure appreciate everyone spending the last couple of days with us and all your great questions and feedback. And
Yes.
we also love to hear what you're all doing as well. So thank you for chiming in the chat and letting us know. Yeah, bingo. Ooh, a bingo would be fun. I did a bingo game and it always fell right near Halloween. And I would always take all my kids' candy, yeah, it was kind of mean. They'd go sleep, but it's all the candy that they didn't need all that. They had so much candy all the time. So I'd take it in as prizes for the bingo. We do Oxidation State bingo. And it was a really fun game. We had the kids loved it. But I think they got the biggest kick out of knowing that I was stealing my kids' Halloween candy for their prizes. And every year they'd be like, Mrs. Nern, how do you sleep at night? And I'd be like, I sleep just fine at night because they don't have the candy and they're not up on, and they were just outraged, but it was so fun.
It was funny.
Ooh.
Oh, there you go.
What was that? I saw the tool and die. Aluminum circles that were just, oh, I tell you what, that is using your resources. That is awesome.
All right.
Oh, and then first year teaching middle school. Oh, so good luck. And thank you for being a middle school teacher.
And don't forget, it's if you start going through these things and starting to prep for it and teach it, and you can't remember something, a little confused, it didn't make sense, then give us a shout out, give us a holler.
Yeah,
we'll help you. We'll do what we can.
Ooh, mouse stamps. That's a good idea. Like it, Marcy. That's good. Oh, that's so neat. I had a kid that had welded one year. They welded a bunch of pieces of metal to make a molecule for me. And that was super cool.
Did they pass welding class?
I think they did pass welding class. Okay. I think they're good.
Well, this was fun.
Yeah, it was.
right, you think we're good?
I think so. Yeah.
No, I'm not seeing any questions come through.
Okay.
Thank you, everybody. And
Yes, thank all of you for participating. And like Stephen and Sarah said, we're here for you beyond this. So please contact us if there's anything we can do. And also contact or let us know if there are ideas you have for future workshops like this. We're always looking for new ideas, things we can do to help you do your job better.
Yeah, this is the last session for the summer here, Marcy, in these that we're doing. We'll put together here in the next week or two different ones. And say we always offer a couple of them in each semester and stuff. And so we'll figure out what those are going to look like. We're still negotiating with the powers that be on campus, what things will look like and won't look like.
Yeah.
What can we do in person? What can't we do? But we always do one or two during the school year, each year too. But then of course we're back next year for that stuff. But yeah. And we always put those out on the lists.
Yeah.
So
Yeah, I'll do a feedback and give you a link. We can do that. We can add that to the Google or to that Google Doc. Yep.
and we will have something virtual, we promise.
Yeah.
Yeah. I think we'd be in trouble now if we didn't. Okay. Well, everybody have a great rest of your day. Have a great weekend. Have a great rest of your summer. And please stay in touch.
Oh, I thought it was gonna be like something cool,
A sign off.
Please, stay in touch. Oh yeah, that's so cool. That's so important. Bill, you got to work on that. You need a tagline.
A tagline.
Whatever you do, whatever you do. Work on it.
The only tagline I always remember is Cowboy Bob's.
Well,
If you don't have anything nice to say, don't say anything at all. Yeah,
That's the way the cookie.
that's the way. Stay tuned for the rest of the story. All right.
goodbye.
I forgot to stop the recording, man. That